Hello and welcome to our linear algebra lecture notes for section 2.5 matrix factorizations. The basic idea behind this is that a factorization of a matrix is just a way to write a matrix as a product of two or more matrices. And really we're seeing this as a warm-up to some of the things that we'll do much later in this school year. But for now, we'll look at one specific kind of matrix factorization called the LU factorization. And the basic idea behind this is you just take a matrix and you write it into a product of two different matrices. So this is a little bit different from block matrices that we did last time, where you took the matrix itself and just kind of grouped the entries in it. Here we're actually multiplying two matrices. The first one is going to be lower triangular, and what that means is that all of the entries that are non-zero are below the main diagonal or on the main diagonal, and everything above the main diagonal is 0. So we have a matrix like that. So we have something with some zeros in the upper right corner, and then typically you'll see ones along the diagonal and then some non-zero stuff below the diagonal times an echelon form of your matrix. So you might have, something like this. Let's see, I'm writing these stars to mean that they might be kind of anything. So maybe we have a matrix that looks like that. So there is a lower triangular matrix and an echelon form of your matrix A. Okay, so our first quiz asks us to figure out which is an LU factorization of this particular matrix here. All of these are products that give you A, but only one of them starts with a lower triangular matrix and ends with something that's an echelon form of A. So hopefully you can sort that out. Okay, now why is this useful? Well, if we have a matrix of the form, or if we have a matrix equation of the form AX equals B, and we know A is actually equal to LU, then what we can do is we can actually group that UX. And now we can solve, instead of solving AX equals B, which we would typically do with an augmented matrix, we can solve L times something, we'll call it Y, so that Y is our UX, equals B. And so we solve for Y. And that's easier to do because L has a bunch of zeros. So just like last time, zeros are our friends. So zeros help us work with matrices more easily. So now we found Y, and now we know, as we said above, that Y equals U times X. So now we can solve the equation UX equals Y, which is now easy to solve for X because we're already dealing with an echelon form of our matrix. We don't have so much more work to do. So basically, having this factorization takes us from having to solve an augmented matrix with like a whole bunch of row reductions to just a few row reductions to get us to a solution. And let's see that in action. That'll be the last thing for this worksheet, so it's a fairly short one. So we want to solve the equation AX equals B, where A and B are given, and we're already given our L and our U. And so the first thing we do is we solve L times something equals B. So we can write an augmented matrix. Rather than using A, we directly use L. And you can see that this is close to reduced echelon form. We just need to we'll add row 1 to row 2. And we get 0, 1, 0, negative 2. And then we may as well take row 3 and subtract out 2 times row 1. So we're combining two operations. 6 minus 4 is 2. So that's already telling us that y1 is 2, y2 is negative 2, and y3 equals 2. And you might be saying, wait, what are these y1, y2, y3s? Well, remember we said L times y equals b. And so y is a vector, y1, y2, y3. And so now what we have, just to write things down, that's what goes in here for u times x. So let's rewrite this equation then. This 4, 3, negative 5. Actually, you know what? Maybe it's worth seeing this. So what we had here then was 1, 0, 0, negative 1, 1, 0, 2, 0, 1 times this 2, negative 2, 2 gave us our b, our 2, negative 4, 6. That's the work we did up above. And so now we just want to know how to pull out this part, which is really supposed to be our u times x. And so we need this u times x to equal that 2, negative 2, 2. So again, we can do an augmented matrix. And now we already have echelon form, so it's not going to take us too long to do reduced echelon form. I'm going to go ahead and do 2 operations at once, so we'll leave that first row alone. And we get 0, 1, negative 1, 1, and 0, 0, 1, 1. And now finally we can start making zeros up above. So remember that for going from echelon to reduced echelon, we need to make the leading entries 1s and everything above them 0s. So let's go ahead and take row 2 and add row 3 to it. So row 3 is good, and then when we do this, row 2 is good, and we may as well just operate on row 1. Let's do row 1 minus 3 row 2 to get rid of this 3 here. So we have 4, 0, that negative 5 isn't going to change, but that 2 minus 3 times 2, so 2 minus 6 gives us a negative 4. And then finally, let's do row 1 minus 5 row 3. And so let's go ahead and write down row, oops. Okay, so rows 2 and 3 are set. So now we do row 1 minus 5 row 3. So we have negative 4 minus 5 is going to give us a negative 9. And did I do that right? Okay. And so finally, we just need to divide row 1 by 4. I'm a little worried that I made a small error. But I may have made a small error in my notes when I was formulating this earlier. Okay, so in any case then, assuming that I did that row reduction right, and if I did it wrong, let me know, double check this for yourselves, and know that we all make mistakes, and let that help you feel a little better if you make some small errors with your row reductions. But the point is that now our solution is x1 equals negative 9/4, x2 equals 2, x3 equals 1. And so to pull that back to our original situation, that's telling us that if we multiply this matrix A, and you can check your answer by doing this, times what we got, which was negative 9/4 to 1, then we should get back our B, which is 2, negative 4, and 6. And it does appear that I made some sort of error. How can I tell? Well, we multiply negative 9 first times 4, so that's negative 9 plus 6 gives us negative 3 plus negative 5 would give us a negative 8. So we made a mistake. Let's go back and see if we can find it. So let's see. So we divided by 2, we divided by negative 2. This would be fun for you guys to be here with me because you might have noticed it as I went along. Row 2 plus row 3 gives us a 2. Row 1 minus 3 row 2. So we had I think what happened is I combined too many steps here. So let's do one step at a time. And that's one of the ways you can tell on your row reductions if you're needing to slow it down. If you're making mistakes, then slow down and don't combine so much. So let's just operate on row 2 and pull those out separately. So it didn't save us time in the long run, huh? So we do row 2 plus row 3, and that I believe is correct. Now let's do row 1 minus 3 row 2 and see what we get. 4, 0, that negative 5 stays the same, and we get 2 minus 6, which is negative 4. And now we are going to do row 1 plus 5 row 3. I feel like that might be where we made an error. So I have 4, 0, 0, and then negative 4 plus 5 is 1. And then I'm just going to write my other entries down, and this gives us what I got when I did it before. So row 1 divided by 4, we get 1, 0, 0, 1 fourth, 0, 1, 0, 2, 0, 0, 1, 1. And so in fact, our answer is x1 equals 1 fourth, x2 equals 2, and x3 equals 1. And so maybe if we try that, so we have 1 fourth, 2, oops, and 1, and we'll just test the first one. So we get 4 times 1 fourth, so that's 1 plus 6, which is 7 minus 5 is 2. Okay, and you could test the other ones, but I'm going to stop there.